I'm going to start it out just as normal. Okay, so we're going to talk about the antiderivative today. Yeah, no, super. I'm not going to get a billion. I'm never going to get a billion YouTube followers.
I already put like 11 Panther bucks in your thing. You owe.
I put in
Okay.
15, so.
All right.
I put in 7.
Great. Clearly, you guys overwhelmingly want me to lose my beard.
It's going to be funny when some of us have more facial hair than you.
Absolutely. Absolutely. Okay. So the antiderivative. All right. So what the antiderivative is first. So if we have some function f of x, the antiderivative of f of x so f of x has an antiderivative we'll call it the antiderivative g of x. And we'll say so that f of x is equal to g prime of x. So essentially, like, we're going backwards from everything we were doing last chapter. So last chapter we were taking a function and finding its derivative, and most of what we were doing with the derivative was using either the power rule, where you would take the power, knock it down in front, or put it down in front and then knock the power down. We were using the product rule, where it was f prime g plus g prime f, the quotient rule, f prime g minus g prime f over g squared, the chain rule, or some combination of those. So this time we're going to be working backwards. And for today, for the most part, we're only going to be using the power rule. Yeah.
Okay, so with the antiderivative, like with the derivative, when we did that, there were the numbers that like dropped off and like became 0, so we didn't have them. How do you
incorporate those back in?
Yeah,
exactly. So I'm very glad you guys asked that without me needing to bring it up. So let's take a look at an example here first. So let's say that we have something that's really, really simple. So like 2x. If I want to find the antiderivative of 2x, so your instructions would be something like find the...
You shut your window when you check, please?
Yeah, absolutely. Oops, that's not shutting it. That's the opposite of shutting it. Find the antiderivative of 2x. So the antiderivative of 2x, so I want to take this backwards. So right now this is x to the first. So I know that the antiderivative is going to need to be x to the second. And then I need to take into account what would have happened to the number in front. So this 2 would have gone up to the power. And I... No, the antiderivative.
So you just reverse it.
Right, so I'm going backwards. Yeah, I know. So what you're feeling in your head right now, Kim, is cognitive dissonance, and that's how you grow your brain cells. Okay.
Well, that was about 4 words that are too big for my vocabulary. So
Okay. So the antiderivative of 2x is x. The antiderivative of 2x is x squared. All right. So now, okay, guys, quiet for a second. So the antiderivative of 2x is x squared. Now that's true, but I could also say that the antiderivative of 2x is x squared plus 5. Because if I do the derivative of x squared plus 5, the 5 part falls off. So the derivative of x squared plus 5 is 2x. I could also say that the antiderivative of 2x is x squared plus 7. These two things are both the antiderivative of 2x. Do you guys see that? Because if I were to do the derivative of this one, it would be 2x, and the derivative of this one is 2x.
As long as you don't add another x in there, it could be any number you could add or subtract behind it.
Right. I could also say the antiderivative of 2x is x squared minus 1 billion. Right?
37.
Sure, because that's my favorite number, but yeah. So now, in math, in order to accommodate the fact that there could be this constant that's being thrown onto the back here, what we say when we do the antiderivative is we're just going to do x squared plus c, where c is just some constant. So this is what we say in general terms. Because that c, that constant, could be anything. It could be nothing, but it could be anything. So when we're doing the antiderivative, until we know more information, we're just going to throw a plus c onto the back of every one of them. Yeah?
So would you use this, so like you know how you were talking with the derivative, you use that for the one specific point?
Mm-hmm.
Would this be for finding like the boxes? Like,
Yes.
okay.
So
So is that why that number is there at the end, because you can have an unlimited amount of boxes in something? Or?
it's more so that, so like when we're finding the area underneath the curve could be here or it could be here. And it's finding out, like, the curve could be shifted up.
Oh, okay.
And it's how much it could be shifted up. Okay. So there's some rules I'm going to give you guys for antiderivatives here. That's going to make your life a tiny bit easier. Again, I made your assignment a little bit too easy, so you might not need to use these rules, but I'm going to give them to you. You can choose to use them. You can choose not to use them. So here we go. So we got function on the left-hand side, and then antiderivative on the right-hand side. Function, antiderivative. All right, so if a function looks like x to the n power, then the antiderivative is going to look like x to the n plus 1 over n plus 1. And I'll show you how to use that in a second. If a function looks like 1 over x, then the antiderivative looks like the natural log of x. And this is my favorite, and it's probably going to be your favorite too, because it shows up on your assignment. If a function looks like e to the x, then that's right, the antiderivative is e to the x. Okay. And then later in the week, we'll talk about the trig functions and their antiderivatives and their derivatives.
Wait, scientists can actually add those?
Yeah. I've left those alone until now. No longer shall I leave them alone. We're going to dive headfirst into those this week.
You mean our place will actually be useful?
Yeah. Okay.
What would you, just out of curiosity, what would you use the derivative of sine plus 1
Finding the area under the curve. All right.
Okay.
So, here's what we're going to do today. I'm going to pass out your assignment and we're going to take a look at this.
Oh, it's handwritten.
Well, half of it is.
You didn't even write the full font.
Well, half of it's handwritten and half of it's computer generated.
God, I couldn't imagine.
Okay. So, there's a backside, yes. Half of it's handwritten, half of it's computer generated. So on the front side, we're finding the antiderivative. 1, 2, and 3 are pretty easy, so I'm going to skip over doing those with you guys, especially since I did number 1 on the board. So let's take a look at number 4, which is where it starts getting difficult. Or we can jump down to one of the more difficult ones if you guys want to. So let's look at number 4, or maybe 5 or 11. Okay, we'll start with 4. So you have to do the antiderivative of x to the 5th. So we're going to use that power rule I gave you guys. So the function, in this case, you're using 5 where n goes. So it's x to the 5th where, so 5 goes where n goes, and then you're doing the antiderivative of that. So it's going to be x to the n plus 1, and so n plus 1 in this case would be
6.
over 6. And then what do you have to add to the end of it? So plus c. So it's going to be x to the 6th over 6 plus c. And you have to add that c because there could be a constant added to it that when you do the derivative, the constant goes away. So number 4 is x to the 6th over 6 plus c.
So on 5, does that 2 go away?
So let's look at what happens on number 5. So let's leave the 2 alone for now. Let's just focus on the x to the 3rd. So the x to the 3rd is going to turn into x to the, and then it's all going to be over, and the 2 and the 4 cancels down to what?
Over 2.
1 over 2. So it's going to be x to the fourth over 2
Let's see.
plus c.
Wait, why?
Okay, let's talk about y. So you're going to focus on the power for a moment. I'm going to leave the 2 alone. So x to the third turns into x to the fourth over, and then whatever that number was, you're going to put down here. We're going to put the 2 back where it was,
Why do you put this one
because that's what the power rule says to do.
on? Oh.
So you're going to have it be x to the whatever power it was plus 1 over whatever that power was. Right. And then I just put the 2 back where it was, and now the 2 and the 4 can simplify to be what?
X to the fourth over 2.
Right, so 1 over 2, I don't need to put the 1 down because it's just 1, so it's over 2, and then plus c, because they all have plus c as part of their answer. Kind of, sort of,
Okay.
and then that's it.
What about 7?
Sure, let's look at 7. 7 is actually pretty easy.
But then I don't know what to do with 2.
With the 2, let's talk about what to do with the 2. So, if there's no x already there, I'm going to pretend that the x that's there is x to the 0. All right? So if there's no x already there, we're going to pretend that there is an x there, but it's x to the 0.
This is 1, right?
So yeah, because anything to the 0 power is 1. So the derivative of, or the antiderivative of e to the x is e to the x. All right, you're with me there. So minus, I'm going to pretend, I'm going to come back to the 2 in a second. So this is going to be x to the, when I do the antiderivative using the power thing.
Negative first, or first.
First, because I'm not doing the derivative, I'm doing the antiderivative, over,
1.
1,
so I don't need to do the over part then, right?
right.
Okay, is this hurting your brain yet?
Yep.
Isn't this awesome?
No.
And then I'm just going to put the 2 back in front of it.
Okay.
And now wait, there's one more thing I need to do, plus c.
Couldn't I just put an X behind that?
Yeah, you don't have to have x to the first, you can put just plain old x.
Could I have done that at the beginning without figuring all of that?
Well, I'm explaining why it's there.
Assume the steps in case you get confused.
Yeah.
It's not always just going to be that easy.
Right. Yeah, no, very wise words. Wise words.
So what about 11?
What about 11? Yeah, sure, let's just jump around everywhere. So, number 11. So, based on what happened to the 2, what do you think is going to happen to the 5?
It's going to be 5x.
So, 5x. Now, let's talk about that 2 over x.
This is where we panic and start crying, right?
No, so, I'm going to pretend that this is 2.
Is it natural log?
2x.
Yeah.
How?
So, it's 2 times
The
natural
natural log
log x
plus c.
plus c. All right.
Can we do number 8?
Sure.
Yeah, I'm kind of excited here.
So the 9 halves we're going to leave alone for a second, and the x squared is going to turn into over. So x to the third over
3.
3. And then I'm going to write the 9 over 2 here, and then these two, the 2 and the 3 are going to multiply themselves out.
6.
Right. So it becomes 9x to the third over 6.
Or 3 halves x to the third.
Ooh, good. And then plus, and then based on what happened to the 2 and the 5, what happened?
Plus c.
Plus 3x plus c.
So 3 halves x.
So 3x to the third over 2 plus 3x plus c. I got to tell you, I'm real glad I decided to separate this out into its own lesson.
Yeah, why is there a 3 on the
Okay, so 9 halves is its own thing.
Yeah.
Okay, so x squared became x to the third because I raised this by 1. And then whatever I raised this to needs to go on the bottom too. So this became x to the third over 3, but there was already a 9 halves there, so I had to multiply, like 9 goes on top, and 2 times 3 goes on bottom because the 3 went down on bottom because this raised to 3, and then 2 times 3 is down there too. So this turns into 9x to the third over 2 times 3, which is 6, and then that simplifies.
3x to the third over.
Sorta, kinda? Tiny bit? Only on days that end in y?